Swayam Prabha. Digital India. Educated India.
All right. Good morning. How's everybody doing? Halfway through the course. Yeah? Okay. So today we will switch gears and talk about modeling of machining and focus mostly on metal machining. That's an area that I have worked on and off for some time. Since we've been talking about material removal processes, including non-conventional or laser-based processes. Obviously, what I'm going to talk about today has very little connection to the laser-based methods, but still very important because machining processes, including conventional machining, is routinely used in industry, all the way from kind of the obvious types of, to produce obvious types of products, aerospace, automotive, even though in the automotive sector today, because of electric vehicles, there are, the manufacturing technologies required are very different, obviously for electric vehicles, but there are still components. You don't have internal combustion engine components, which historically have used metal machining processes, conventional machining processes. But all the way from your mobile phones, if you own an iPhone or even some of the other manufacturers, the back of the iPhone, the actual housing is aluminum actually, and I think some of them maybe even titanium. I don't know. It depends on how much you're willing to pay. But those are machined. They are actually diamond machined using diamond tools. So it's still a very relevant, very, very relevant process, certainly in the aerospace sector, biomedical sector, and many other sectors, even though machining is a very old process, right? It's not new, just like casting, not a new process, but extremely relevant, still being innovated on. And even though it's being used extensively, or is used extensively in practice and has been used extensively in practice, it is still a very complex process. As simple as it seems. You see on a lathe, you go use a lathe and you cut something and say, oh, fine, I can do this, or a milling process or whatever, drilling. All these seem very simple, okay, in principle. But the underlying mechanics of these processes is very complex, which is why, while our understanding has advanced to a point today where we do have some commercial simulation tools that you can actually purchase to simulate metal machining, to actually simulate three-dimensional machining operations in a computationally efficient manner is not easy to do, even to this day. Okay, so we'll talk about what is involved in trying to model these types of processes. What kinds of things do you need to know? What are some of the issues, as well as what kinds of things can we do? What has scientific advancement in modeling, understanding of the physical process and modeling, brought us to today, and what are some capabilities that exist? What are some limitations? So we'll talk about those kinds of things. And again, like last time, they stopped me. If you have questions, we'll have a discussion. Hopefully today I don't finish as early as yesterday, right? And if we do, then we will have an open discussion, okay? So this is kind of the agenda for my lecture today. So I kind of I already made some comments, introductory comments about the importance of machining and metal machining in particular. But we'll talk about the role of constitutive modeling, describing the behavior of the material subjected to, cutting operations, modeling of friction, which is an important aspect. In most manufacturing processes which involve contact between a tool and the workpiece, friction is important. Certainly in machining, frictional conditions can be extreme. And then we'll talk a little bit about microstructure modeling as to where things stand being able to, it's not just enough for me to be able to predict things like forces, chip formation, and things of that nature. In the end, what are we interested in any manufacturing process? We're interested in being able to produce a component with the required geometry, the required surface quality, and microstructure and mechanical properties. All of those things are important, right? But are we there today for us to be able to actually accurately model and simulate, or model and accurately simulate what happens, right? We are not there completely. We are not there, to be honest. But we have made advancements. So where do we stand today? And what are some open questions that that might be of interest for you if you want to pursue research in this area, etc. So that's kind of the agenda. So I've already kind of explained to you briefly that these are very relevant. Machining or metal cutting, as old as the process technology is, it's very relevant. Industry uses it extensively. Okay, and so of course, as industry uses it, but as with any other manufacturing process where you don't want to rely on trial and error experimentation to determine under what conditions you will get the desired output, right? Machining is no different. Here again, we want to be able to be intelligent about how do we arrive at the conditions which will give us the end result that we are interested in. So in other words, solving the inverse problem. That is, I want certain output, I want certain surface quality, certain mechanical properties, certain geometry, okay, that satisfies some tolerance requirements. What should the knobs be? What knobs should I turn and how much should I turn them in order for me to get there? That's the inverse problem. That's the holy grail in any research for that matter, certainly in all manufacturing process research for sure. So that's the objective, but to solve that inverse problem is a much more difficult problem. But before we can solve that problem, at least can we answer the forward problem? That is, given certain inputs, can we predict the output, right? That is the forward problem. And we'll start there, right? And that's where much of the focus has been to date. And you see some pictures of turning. Let me see if I can get a pointer. So you see a typical longitudinal turning operation. You see here a simulation, a 3D simulation or a snapshot of a 3D simulation that is basically simulating the interaction between a cutting edge, such as in a turning process, and a rotating workpiece. Okay, it's a snapshot. This is using a commercial tool that's actually available. It's a computational mechanics-based simulation tool called Advantage. That's one. There are others as well that you can purchase. This is for a milling operation, as you can see. Then this is showing you simulation. Obviously, you don't see the tool, but you see the chips flying out. This is showing you simulation of a milling operation, right? But to do these simulations in 3 dimensions, as shown here, is very, very computationally intensive. It can take you days just to simulate one revolution of the tool, right? Hours for sure, but days typically. Well, that's not very practical, right? If you're the engineer, you've been given a task of figuring out what conditions to machine this part in, then, your boss won't be happy if you say it's going to take me a week to run one simulation. Forget about optimization. If you have to optimize, you have to turn many knobs, different settings to determine which is the best. Just if one combination takes you a week, then that's not a very good situation, right? So, but that's today a limitation in terms of how efficiently you can do this. But the fact that you can do this is an advancement. We couldn't do this even, right? Till not long ago. But there are many applications. These tools are being used today in industry, right? They're being used for tool design. As most of you who have had any exposure to metal cutting, whether it's turning, milling, drilling, doesn't matter, any of those operations, you've seen cutting tools are complex geometries, all the way from even lathe tools. The disposable inserts have all kinds of geometries, and you wonder how they came up with those geometries, right? They have all kinds of chip breaker control geometries that are designed in them. And much of that, to a large extent, historically, has been done empirically, experimenting. The basic concept is very simple. You have all these bumps and grooves on the surface of the top surface of the tool to actually increase the curl of the chip. Okay, that's very simple, right? If you take a beam and bend it, if you bend it a lot, it's going to crack and fail because of tensile stresses on the outer surface. That's the basic idea, but there are many variations of it. But they have done it through trial and error, which is not a very efficient way of doing it. So now today, because these tools have been developed, simulation tools, they can use these tools to at least minimize the trial and error process, right? It's cheaper for me to run simulations than it is for me to go to a machine shop or to actual machine and make tools. The making process of the tool making process itself is time consuming. Okay, and if you want to try 100 different geometries, it's going to take you enormous amount of time and money. So with simulation, you can do it much more easily. So that's the motivation, right? So they're using it for tool design. They're using it for designing chip control geometries. Obviously, chip is quote unquote waste material, right? I mean, it's material that is removed. It's not waste in the sense that today you want to recycle as much of that as possible, right? And in the aerospace industry, where almost 95, 96, 97% of the volume of metal is machined away, right? If you think of wings of airplanes made out of aluminum, structural members, they are machined from a block, and 95 to 97% is machined away. So you generate lots of chips. Now, those are expensive materials, right? If it's a high-strength aluminum or it's titanium, then you can't just dispose them. So there'll be train loads of chips that actually come into a factory, take it away, clean it, and then try to recycle it. Certainly, aluminum is theoretically 100% recyclable. So, they would like to recycle as much as possible. So chip control is important because you want to be able to handle these chips. You don't want long, stringy chips that, basically get entangled around the workpiece and damage the part and so forth. One of the most useful tools or useful aspects of these simulation tools is being able to do this process parameter optimization. What feeds, speeds, and depths of cut should I select? This is a common issue. And usually there are some recommended values. When you purchase a tool from a manufacturer, they will give you some recommendations, right? Which they have determined experimentally, but they have determined on some machine. Your machine may be older machine, newer machine, different machine. There's no guarantee those values work. You start with that, and then most machinists will basically tune it, which takes, again, some trial and error on their part. So if you have software like this that allows you to arrive very quickly at some set point and then fine-tune very little, minimize the amount of experimental effort, that's very useful. Tool life analysis. This is still a challenge to be able to truly predict tool life. Okay, that is, how long will this tool last before it no longer is able to machine according to the quality requirements that I might have in my application. Tool life is still not easy, because any wear processes has a lot of stochasticity associated with it, so it's not that simple. Thermal management, this is important because of multiple reasons. One is that temperature affects tool wear. That's one reason. But the other reason also is that you don't want to have too much heat going into the workpiece, which will damage the part itself, microstructurally alter it, or dimensionally alter it, whatever the case may be. And then finally, as I said, surface integrity. What kind of residual stresses are produced? What kind of metallurgical changes might be produced, which may or may not be desirable? All of these things we want to be able to do in practice, right? And I want to be able to simulate. As engineers and scientists, our goal should be, we want to use knowledge of the physics of the process to arrive at the answer as much as possible. It's not possible 100% of the time, or most of the time it's not 100% possible, but to the extent we can utilize scientific understanding, you minimize the trial and error portion of this process. So that's really the motivation for us to be able to accurately simulate. Now, um, what makes this process complex, right? What makes it complex to model and analyze, right? And you can see here that in this simple video that shows you essentially a slow motion video of the cutting process of some polycrystalline metal. And this is the simplest type of cutting process. It is called orthogonal cutting. It's taking a wedge-shaped tool and removing a layer of material. That's what you see. You can see the kind of the severe plastic deformation of the metal that the metal is undergoing, right? Undeformed material approaches the tip of the tool, and then as soon as it reaches a certain point, it shears heavily, okay? Heavily sheared, which is denoted, there's an approximation of what is happening in the video that is shown in that sketch on the right-hand side, which shows you a zone, a pink-colored zone here, that is the region where much of the shearing is taking place, right? And then a chip forms, this chip forms, and it's flowing up. And notice here, the contact between the tool and the chip is quite intimate. It's very intimate, okay? Extremely intimate before it curls away and there is separation, right? So obviously there is relative motion between the chip and the tool. There is also, of course, the shearing going on. At the very minimum, these two things are happening. But as the tool wears, then there could be rubbing also at the bottom here in the flank of the tool. So process can be pretty complicated. And given that the material is being subjected to such extreme deformation, okay, and it's not just deformation in terms of amount of plastic strain that the material is undergoing, right? It is actually being subjected to very high rates of deformation, right? This is slowed down in this video. Even a conventional cutting operation that you might see on a lathe, the plastic strains that the material is being subjected to are very high. They can be as high as 4, 5, 6 plastic strain, okay? Shear strain, okay, can be very, very high. And when I say plastic strain, I mean the effective strain, okay? The shear strain correspondingly is very high as well. And the rates at which the material is being strained, that is the strain rate, is few orders of magnitude greater than what you experience in a tension test, a typical tension test, right? Which all of you are familiar with tension and compression tests, which is done in the lab. Those are performed at strain rates. You're pulling the material at extremely low rates. You're talking of 10 raised to minus 2 per second or something of that order of magnitude, right? Or even 10 raised to minus 3 per second. Very slow pulling of the material. The material here is being subjected to strain rates on the order of 10 raised to 3 to 10 raised to 5 per second, sometimes even greater, okay? So you're talking of 4, 5, 6 orders of magnitude greater than in a tension test. And if you use tension test to determine the yield strength of the material, right, it's inadequate to characterize what happens in machining. You can't just take the yield strength of a material obtained from a simple tension test and use it to describe what the material will be subjected to in a cutting operation, okay? Also, the strain rates in a tension test are very low, as I already said. Okay, amount of strain is also low. So, because in a typical tension test, you're talking of strains for a ductile material that are probably on the order of 0.4, 0.5, 0.6, maybe depends on the ductility, not 2, 3, 4, 5, nothing like that, right? So, much higher strains. Okay, so as simple as the process looks from the outside, you can cut. What's going on inside is very complicated. That's what makes it difficult to model, okay? But to be able to model, I need many things. I need to be able to describe how does this material behave under these conditions, right? Under these strains, strain rates, and temperatures. If you have cut metal, depending on what you have cut and how aggressively you may have cut, I'm sure you have seen sometimes the tool glowing. It's red hot, workpieces with chips are red hot, right? That's because you used a very aggressive cutting condition, right? Or you're cutting some very difficult to cut material. That's a lot of, most of the mechanical energy, over 95% of the mechanical energy that is being expended in a cutting process, a metal cutting process, is converted to heat. Okay, energy is conserved, but it's converted to heat, and that is what causes the chip to glow and so on and so forth, right? Depending on how aggressively you cut. So you need to be able to describe the behavior of this material, which is what I'm calling constitutive properties of the material behavior, right? Stress-strain relationship, if you will, or stress, strain, strain rate, and temperature relationship in the most general case, or in a more general case, I shouldn't say most general, more general case, you need to be able to describe that. Then you also need to describe the frictional conditions that are there. This chip is sliding up on the, or appears to be sliding up on the face of the tool. So there is frictional interaction taking place at least there. Maybe if there is wear on the tool, then there will also be contact there. All of these have to be described. And that friction description is still very complicated. It's not your simple Coulomb friction that you are all familiar with, right, from physics. It's not as simple as that. Thermal properties. Well, I mentioned to you temperature rises, right? And you know very well that the temperature rise in the tool and the workpiece and the chip will be a function of the thermophysical properties of the materials, right? So what are those thermophysical properties? What kind of properties am I referring to when I say thermophysical properties? Thermal conductivity is one, right? Thermal conductivity is one. What about other? I'm sorry? Thermal expansion, potentially, but for certain aspects of the problem, yes, but not for the plastic deformation. We are talking of severe plastic deformation, right? So just thermal expansion can occur, most certainly, and what it'll affect would be the depth of cut and so forth. But I'm really talking about something that allows me to describe accurately how this material is behaving, right? So thermal conductivity certainly is one, okay? Specific heat, right? Because ability to actually conduct heat away, or, the heat capacity of the material matters, right? So that will determine the temperature rise in the material. So these kinds of thermophysical, and many of these, of course, both of them, in fact, thermal conductivity and the specific heat capacity, are functions of temperatures themselves, right? They change with temperature. So you have to be able to describe that because you're producing very high temperatures, depending on what you're cutting. If you're cutting titanium, you may have temperatures in excess of 400, 500, 600 degrees, okay? It depends on what it is, right? What you're cutting. So this has to be described. Thermal properties have to be described, okay? Contact resistance, or the thermal contact resistance and things of that nature also. In reality, they have to be, although they don't really consider that often. And then, of course, the microstructure. The starting microstructure of the material and how the microstructure changes. Ideally, I want to be able to also model and simulate the change in microstructure. Okay, why? Because microstructure is what determines the mechanical properties, right? So how I modify the microstructure of the machine surface, okay, will tell me what kind of hardness and strength characteristics that machine component will exhibit, right? At least in the near surface region. So many things are required. I need to be able to describe plastic flow of the material, friction, heat generation, and transport. And also chip is being separated, right, from the material, right? So you're creating new surfaces as you're doing this. All that has to be considered. So it's not as simple anymore, okay? All right, I already pointed to you that when you're deforming the material, this is basically a more magnified view of what's happening, or an idealization of what you saw in that video, showing that there is a zone of material that is being deformed plastically at very high strain rates. And that deformation, it's happening in very short time durations. And that energy that is expended in deforming the material is converted to heat. As a result, there is a temperature rise. So I need to be able to describe the material behavior as a function of strain rate, and temperature. I already mentioned to you, the strains can be very high in machining, 1 to 10, well in excess of what happens in a typical tension test or even a compression test. Strain rates, very high, 10 raised to 4 to 10 raised to 6 per second. Temperatures can be a wide range depending on what you're cutting. It could be relatively low if you're cutting aluminum to something like titanium or Inconel, super alloys, much higher, right? And these pictures are basically showing you what's going on in the material. There are more sophisticated tools today, experimental methods to actually probe the behavior of the material in situ, right? Historically, people use the kind of high-speed videos that you saw there, or they superimposed some sort of a grid, okay, but only for very low velocity type of cutting experiments. But under conventional cutting conditions that you use in practice, it's harder to actually do those kind of experiments. But today there are techniques. What you see here is basically something called particle imaging velocimetry, okay, which fluid mechanicians use. Particle imaging velocimetry, PIV, okay. I mean, sometimes, particle imaging velocimetry is a technique that fluid mechanicians have used for a long time to be able to experimentally analyze flow of fluids, okay, and analyze the boundary layer between flowing fluid and the solid wall, okay, things of that nature. So essentially, you're all familiar with from fluid mechanics streamlines, like so analogous to streamlines. You can observe streamlines using particle imaging velocimetry, okay, but you can think of these as streak lines. In other words, a particle in the material, this is homogeneous, it's not fluid, it's a solid. But so if you treat the solid as flowing fluid, you can use similar techniques to be able to see how that fluid particle, in this case a solid particle, is changing, right, its position as a function of time. And from there you can estimate strains, strain rates in situ. And so you will be able to describe the distribution. What you see here is just that, okay? Sometimes people also call this differential imaging, it's called DIC, digital image correlation, sorry, thank you. Digital image correlation, okay? So digital image correlation is a technique that is used in combination with particle imaging velocimetry that allows you to image and analyze the image using digital image correlation, okay? That is what is done. So there are techniques today that give us much greater insights into what the material is experiencing during cutting, okay? Let's see. Okay, I think this is the only point I want to make. There's more information on these slides that we need to really delve into in great detail. Measuring the deformation field in machining, okay, as well as measuring temperatures. So this is important. Measuring temperatures is not easy. Probably one of the most difficult things to measure in cutting is temperatures. And it's not just the average temperature that I'm interested in, because the deformation, as you saw, is very inhomogeneous or non-uniform, right? The strains and the strain rates, and therefore the temperatures within the material as it's deforming vary from point to point, right? So there is, if you go back to that video for a second, okay, let me see if I can play this again. Okay, so you can see here, it's not that every point everywhere is experiencing the same amount of strain rate and deforming at the same rate. So therefore, the temperatures are not going to be the same either. So there is a distribution. Typically, what you find is that the strains are very high, right, at near close to the tip of the tool. Temperatures can also be very high. Temperatures tend to be higher up here on the face of the tool, because there is also not only energy dissipation due to plastic deformation, but there is also frictional energy dissipation between the chip and the tool, right? So as a consequence, measuring temperatures inside is not easy. This has been done for a long time using thermocouples and other types of techniques, including using infrared thermography techniques. But, emissivity changes with temperature. So this makes it a bit more challenging. And also to get sufficient spatial resolution of temperature measurement is not easy. People have done this. There are papers, etc., that you can find. This is actually one of the most sophisticated measurement systems that was developed for temperature measurement by the National Institute of Standards and Technology in the US. And there's a paper that you can look at that describes what all they did to be able to actually do temperature measurement at sufficiently high resolution in a cutting operation, okay? And they're able to measure temperatures, okay? What am I interested in? I'm interested in the temperature throughout the deformation zone, everywhere, including in the tool as well, okay? That's really what I need to know, frankly, if I want to be able to predict, say something about the, how is the energy that is being dissipated? Where is it going? How much of it is going into the tool? How much of it is going into the workpiece? How much of it is being carried away by the chip? How much of it is being radiated or convected away by the environment, right? Or into the environment. All of those questions to answer, not simple to do, and only measurements can help you do that. That's not easy to do, but people have been able to do some of these types of things. All right. What else is important? Not only is it enough to know what is the amount of deformation, strain that the material is being subjected to, and the rate at which the material is being strained, and at what temperature the material is as it is being strained at that high rate. You also need to know things like what is the state of stress that a point within the material is subjected to, right? It is not simple shear that the material is undergoing. The material is undergoing multi-axial stress state. It's being subjected to multi-axial stress state. And why is that important? Because it's important because in that state of stress tells you something about how it will fail. All of you here hopefully have some basic understanding of yield criteria, or have you come across in mechanical design? Maybe the second year undergraduates still haven't had machine design or mechanical design yet, right? Probably have not. Okay, so maybe for their benefit, what I will say is this. Think of a piece of metal and I'm going to load it in some way, apply some mechanical load, right? What question do I want to answer? In design, I want to make sure that I've designed this part or object such that this piece of metal, when subjected to complex loading that it may be subjected to in X, Y, Z directions, and shear loading in the most complex case, will not fail, right? If it fails, or what does failure mean in this case? In design, it means it does not yield. It doesn't change its shape permanently. If it changes its shape permanently, then it has failed, right? You don't want your car to deform when you sit on it, right? Or the chair to deform if you sit on it. So that's not desirable. So you design it so that it doesn't fail. How do you determine if it will fail or not when it is subjected to these loads? Well, this is where the notion of yield criteria comes in. Yielding is yielding, just like in a tension test. Go past the elastic limit, it yields, right? That's the yield point. That's what you call the yield point. And beyond that, it deforms, it strain hardens and fails eventually, right? Fractures. So that is just uniaxial tension, simple tension. But if you're talking of a material being subjected to more complex loading in multiple directions, normal loading, shear loading, etc., then I need some way to be able to tell under what combination of loads will it fail. So that they are called yield criteria. There is two commonly used, and you will learn about it if you haven't learned yet, called Tresca yield criterion or von Mises yield criterion, etc. These criterion that basically tell you when you apply some combination of stresses to the material, will it exceed the yield strength of the material in tension, compression, or shear, depending on how you're defining this, right? So such yield criteria are required. Now, having that general understanding that there is a way for me to quantify, I need the state of stress is important for that reason. Will it yield, not yield, okay? Because failure of the material depends on the state of stress also, okay? So without going into more complex discussion, I think just having that understanding that it's not enough for me to describe what the stresses in the material will be when you subject it to certain strain rates and temperatures. But I also want to know what is for that given state of stress, will this material fail or not? Okay. So that is what the point is being made here. Okay. All right. So how do you describe all of this mathematically? If you're going to model it, you have to be able to describe it mathematically, right? So that you can input into your code, software code or program that does it, whether it's a finite element model that you build to solve the problem, or however you want to solve it, right? So there are two types of models. Okay, this is where things get a bit more complicated. So if it is going over your head, please stop me and I will try to explain it at a much higher level, so at least the concept is clear to you. So I have to be able to describe the strength of the material. Sigma here is the strength of the material as a function of strain rate, and temperature, and perhaps other things, maybe even first order derivatives of these quantities in general, and second order and third order, but nobody does it. First order is all we can do, okay, and or we generally do, even in the most sophisticated models. So just be able to say, you're all familiar with stress as a function of strain. You all know in elasticity, Hooke's law, right? At least you know that. So Hooke's law, sigma equals modulus of elasticity times the strain. Well, this is a generalization of it, where sigma is equal to some function of not only strain rate, and temperature, because the material is being deformed at very high rates or at different rates and at some other temperatures than room temperature. Okay, so this is really what this is capturing. Sometimes this is called a flow stress model or a flow stress equation. Flow stress means nothing other than yield stress. You're all familiar with yield strength that you get from a tension test. Well, if it is a strain hardening material, the yield strength changes as a function of strain, right? From a stress strain curve, right? Changes. So this is describing in its most general form the stress strain relationship for the material. Okay, that is what this is saying. So this can be done empirically. You can conduct tests at different strain rates and temperatures, compression tests, typically compression for machining, okay, because material is being subjected to compressive stresses. I mean, not just compressive, it's being subjected to a complex state of stress, but most metals under compression will deform more than in tension. Okay, so essentially compression is used, compression tests at different amounts of deformation, different rates of deformation, and at different temperatures to build an empirical relationship between the stress, strain rate, and temperature. Okay, so think of conducting various experiments, compression experiments at different strain rates, temperatures, taking that data and fitting some model, right? That says, okay, the yield strength changes as a function of strain rate, and temperature. That's all this is saying, okay? That is called a material model, okay? That tells me if I know what the strain is, what the strain rate and temperature, all three things at a given point in the material during cutting, then I can tell you what the strength of the material is at that point. That's all it uses, okay? All right. Now, this is what is most commonly used, okay? Yesterday, I guess one of you asked me or mentioned Johnson-Cook equation or those kind of models. They are nothing but that's one form of this type of a relationship. That's all it is. There are many others, okay? I'll show you some others, okay? Now, this is called a empirical. I think I call it here phenomenological, but I think maybe that's a bit of a misnomer. The best way to describe these are empirical. You're conducting experiments and you're fitting some function to it to describe the behavior of the material. As opposed to what I call physically based models. Okay, what are these physically based models? These are more complicated models, okay? What they describe is the strength of a material or flow stress. Why do I say flow stress? Flow stress is a terminology for those of you at least the second year undergraduate students here. If you think of a tension test, the material past its yield point will flow as it deforms plastically. And hence the flow stress. But flow stress is nothing but the yield strength at a given strain, or strain rate, and temperature. That's all it is, okay? So this physically based model describes the sigma, the flow stress, of the metal as a function of the variables governing the microscale processes responsible for strengthening of the material. Strengthening, and this is maybe where I will use the white board or the green board, I guess, in this case. So something like this, you're all familiar with stress strain curves, okay, that you may get from a tension test or from a compression test, right? Let's say this is the elastic limit. Now, for machining, the elastic region is really not important unless you're trying to predict residual stresses and so forth, okay? Only then it's useful. But this is what you would label typically as the let's not use that. Let's call it, I'll use a different notation. Let's call this sigma, that's the stress strain, and let's call this sigma y, right? Sometimes books will say y, yield strength of the material, right? Okay, so what is happening past the yield point to this material? No, the stress is increasing with strain, right? What is this called? Yeah, it's flow stress, but what is this phenomenon called? I'm sorry? Yes, it's plastic deformation. But what is this increase in flow stress with strain? Strain hardening, or work hardening, or strengthening, right? So what's happening? So this is the strengthening that the slide is talking about, okay? The strengthening, and let's ignore what's in the parentheses, okay, for now. But or maybe not. Maybe we spend a second here. What is happening when a material is undergoing plastic deformation? What is happening inside the material? How many of you here understand what dislocations are? Undergraduates? Okay, all right, good. So you know that material, you need defects in the material for you to actually cause this deformation, plastic deformation. Defects such as dislocations, edge dislocations, screw dislocations, etc. So these dislocations, there is slip phenomenon of slip. When you apply shear loads, these dislocations move within the material. They accommodate the external deformation that you're imposing on it, right? Till they can no longer accommodate when the thing fractures and fails, right? That's what happens. So, but these dislocations, there could be many of them, and they could each essentially interact with each other, okay? So one can collide against the other, and so strengthening is occurring because these dislocations are moving in different directions, these defects, and they interact with each other. So it takes more and more effort for me to cause that dislocation to get past the obstacle, okay? So this is why dislocation obstacle interaction. That's what is happening inside the material that is responsible for this behavior, okay? That's why you see that in a stress strain level, you see that, but inside the material, that is what is happening, okay? Now, strengthening is one aspect. This happens, right? If you do this experiment at room temperature, a tension test or a compression test. But it can also lead to softening if you do it at elevated temperatures, right? So this is at, let's say, at some temperature T1. If I were to do this, if I increase temperature, what's going to happen? The material is going to soften, right? I'm going to probably lower the yield strength of the material. I will lower the yield strength of the material, and I will increase the ductility of the material, the strain to fracture. This point goes out this way, and you can keep doing this, right? So that's softening of the material. The material is getting softer because of temperature. So because I have the most general representation here, right, which is strain, strain rate, and temperature, not just strain, like you are used to in a class, softening can also occur. Strengthening can occur. There are competing processes. Okay, these dislocation interaction will cause strengthening, but higher temperatures will cause the opposite effect. Okay, cause softening. Okay, which will cause these phenomena such as dynamic recovery, recrystallization, etc., can occur at elevated temperatures. So anyway, this is a different way of looking at the stress strain. This is purely empirical, conducting some tests, measuring the yield strength, and fitting some function, versus describing what is really happening inside the material at a microstructural level. Microstructure here being dislocations, within a grain, for example, right? You're dealing with polycrystalline metals. So these equations, without going into great detail, can describe this behavior. So this is called a physically based model because it is describing how the strength of the material changes as a function of strain, strain rate, and temperature, as a function of the dislocation behavior within the material. Okay? This is telling you how the dislocations within the material change as a function of strain, and so on and so forth. Okay? So what is the advantage of this type of a model? It's a much more complicated model for sure, right? This allows me to say something about things like grain size, etc. What will happen after machining to the grain size? In some way, I mean, as an approximation, if I say that, hey, the dislocation density, essentially it's saying that the stress is related to the dislocation density of the material in some sense. Rho is the dislocation density, okay? So it's a more complex way of describing it. This is called a physically based model. So there are two types of models one can do. The advantage of this is really telling me that the macroscopic properties of the material as a function of microscopic properties, okay, microscopic behavior. Okay, I don't want to confuse, and this is, I know, probably way beyond what most of you undergraduates here in this class understand or can understand, so I don't think it's fair to you. And for the more senior students and researchers, you can go to the papers cited here and look at the details, okay? Now, what this table is showing, and I'm sorry, this is not very clear for you to see here, but hopefully you will be able to see in the video, or once these slides are shared, they'll be available. But this is showing you different types of models. These are the empirical models that I talked about. This is the Johnson-Cook model that is basically a fit of the yield strength as a function of strain, strain rate, temperature. There's also modified Johnson-Cook model. Then there are other types of models which are not only empirical, but they also account for the fact that the history of how the material deformed is accounted for. So called strain path dependence models. There's also this power viscosity law. This is simply saying that I have three functions, one describing the strain hardening behavior, one describing the strain rate behavior, hardening behavior, one describing the thermal softening, and multiplying the three, okay? So there are many different type models. Let's not worry about the structure. Let's not worry about the mathematical description. Let's understand the concept, okay? You can go and dig into it later. Versus physically based models. These are microstructurally inspired models, right? Dislocation type of models that are based on what's happening inside the material. So Zereli-Armstrong model is one model that does this, that is inspired by what's happening inside the material. There are other models here that I've listed. MTS is one very common model that people use in the mechanics, computational mechanics area. So there are models available, okay? And it's only very recently, probably in the last 7-8 years, or maybe a decade, people started in machining trying to use these more sophisticated models that describe the strength of the material as a function of microstructure, okay? Yes?
Are these models called as microscale models?
I wouldn't call them multi-scale models. So multi-scale model to me, these are still continuum scale models. They're continuum scale. And for undergraduates, what he's referring to is if you really want to model material behavior down to the atomistic level, at the atoms, right? So then you have modeling techniques that describe how let's say, a bunch of atoms that describe a very, very small portion of that material, what's happening there. That is, you can simulate dislocation, generation, and so on and so forth, and then combine what's happening at that small atomistic scale with something at the mesoscale, right? Which would be something like a crystal plasticity model or something like that, all the way to a continuum scale. Now, we live in the more, as mechanical engineers, we generally live in the real world where we are thinking in terms of macroscopic properties of the material, stress, strain, these kinds of things, right? But there is a way to connect all of these, right? What happens at which you might use a finite element model, that's a continuum scale model. You're solving a continuum model because you're describing values of a function at different points in a space continuously, right? And you're solving it in a discrete form, of course, using finite elements, but you can actually link it down to what happens at the atomistic scale. Those would be called multi-scale models. That is when I'm simulating the macroscopic behavior based on the atomistic changes that are taking place. Very computationally intensive, and also bridging the scales from atom level to grain level to all the way to continuum scale level, where you don't really model the grains individually, is not simple. Okay, but people do this, right? And particularly the computational mechanics people will do this type of stuff. I'm not saying it's not valuable, but as manufacturing engineers, okay, we are interested in getting some answers that are, and a model that can be used in a computationally efficient manner to get an answer quickly. Do I really care what's happening at the atomistic level? As an engineer, you don't. As a scientist, I might care. But as an engineer, I care about, hey, if I turn these knobs, what forces will I get? What temperatures will I get? Things of that nature, right? So that's my take on it. They're still valuable for sure, no question. But they come at a cost for you to be able to do that. And I question the value of that for simulating manufacturing processes, right? For practical benefit, okay? They certainly have academic value and scientific value. All right. So how do people actually measure the properties? I mentioned that you can build one of those two types of models. All of them, even the physically based models, require some data, okay? They require different types of data that has to come from somewhere, but let's not worry about it. Let's focus on the empirical model. That's simple to understand. It's like a stress-strain relationship. You conduct these experiments, compression tests at different strain rates, temperatures, and fit some function, right? That everybody at least can grasp. Wrap your head around it and say, okay, I think I understand what it's like, a regression model in a sense, right? In some sense. Well, let's limit ourselves to that as a way to describe the material behavior, right? Stress-strain behavior of the material. But keep in mind, as I said, in machining, the material is being subjected to very large strains, very large strain rates, and very high temperatures. So I need specialized testing methods to actually get the data that is representative of what the material is being subjected to, okay? Otherwise, that model is useless. It doesn't describe what is happening to the material. So there are many ways to do this, okay? Is there one way that I would say is the best way? I don't think the jury is out on that yet. In other words, we don't know, okay? I can't tell you there is one best way. Historically, most of the models people have built to describe material behavior for machining simulations, that even the software that you might buy, commercial software will have, they use combination of low strain, elevated temperature compression tests, simple compression of a block of material, of that material that you're trying to simulate. They'll conduct experiments at different temperatures, by heating up the part, compressing it till it fails, getting the stress strain curve, from that extracting the yield strength, right? Getting all of that data. At low strain rates, doing that high temperature experiments. And then there is specialized experiments like this called a Kolsky bar, or sometimes also called a split Hopkinson pressure bar, okay? So these are specialized dynamic compression tests. So it's like taking, the best way to describe what these tests do is to take a piece of metal and smash it at very high velocities, okay? Very high velocities. So it's a pressure bar. There's a sample that is placed here between these two bars. These bars are instrumented. One bar is the incident bar. It is incident on this workpiece. So you shoot this bar, literally shoot it. Sometimes this is called a gas gun experiment. You pneumatically actuate this bar almost like a gun. It is like a gun, nothing different, okay? And you shoot it, it hits this sample of the material, and a shock wave is generated that is transmitted through the bar. Since you know the properties of the bar, you can actually you can extract from this the behavior of the material, okay? So very simply put, this is the kind of experiment that you can do. This is a specialized dynamic compression test. If you're used to seeing a simple compression experiment, think of the same thing, but being done at very, very high speeds, okay? That will go up to about 10 raised to 3 per second type of strain rates compared to 10 raised to minus 3 per second. You can see here very low strain rates. Well, they're less than 10 raised to 0. 10 raised to minus 1 would be typical compression test, or 10 raised to 0 per second. But these will go from 10 raised to 2 to 10 raised to 4 per second, okay? At those strain rates, you are deforming the metal, analyzing the stress strain data, and that describes the high strain rate behavior of the material, okay? You can also do it at elevated temperatures. That is, you take the workpiece material, you heat it up, and then you smash it, okay? So you can do those kind of things. Then there is something else called a plate impact. It's called a Taylor anvil on rod impact test. This is a very specialized test. You know, generally people who are interested in ballistic impact, what happens when a bullet or a rocket smashes into metal? When you're designing things that, to shield a building from some sort of a projectile impacting it, right? Then these type of tests would be used to describe, let's say you're designing armor plating or something like that for some application. Then you need these type of experiments. People haven't used this for machining, to the best of my knowledge, but in theory you could use it, okay? But you need these types of experiments, or some combination of these, to get this stress strain rate temperature relationship, okay? So it's not simple, it's not easy, takes time and money to do these experiments, okay? So take that is your understanding that I think you should walk away with. If anything else, that there are techniques, but they're not that simple, but yes, they are available for us to do that. All right, I'm going very slow here, but because I'm afraid that maybe much of this material is probably too much for the undergraduate students, but I'm going to try to get to the more interesting stuff, or at least something that will be easier for you to understand shortly. Let's see, what do I want to say? Yeah, I mean, there are many aspects that are important. You know, when you're describing material behavior, you need to actually also be able, every material has a certain starting microstructure. Think of steels. Steels, depending on the heat treatment, their starting microstructure is different, right? Just because you say, I machined 1045 steel, AIS at 1045 steel or mild steel or whatever, may not be enough. A mild steel, or rather a steel, heat treatable steel, I don't tell you what the heat treatment was, you won't be able to reproduce the behavior of that material, because the heat treatment will change the microstructure properties, and therefore the behavior in machining will be different. So what we are trying to say here is that it is very important, and historically in literature, nobody tells you what the starting microstructure is, right? They may give you the designation, AISI 1045, 50 to 100, whatever, and give you some hardness value. Okay, that's better, but it's still not enough, really, okay? And that's the point I'm making here, that if you really want to do this properly, you have to document what is the starting microstructure. The same material, different heat treatments will behave differently, right? You would expect that. And so machining response will also be different. Okay. All right, let's move on, just to make sure that I'm not going too slow. I'm not sure what happened here. Okay. All right. So what was I trying to do? So this is basically physics-based modeling, okay? This is the other extreme. Now, this is the more complicated stuff, okay? So I'm going to try to explain it try to make it as simple as I can. So this is showing you what is happening to the material in that, let's say, red trapezoidal region that you see there, okay, right? A small element there is undergoing deformation. You saw the video, how it was being deformed. And I have just blown it up and shown you atoms, right? And this is a polycrystalline metal. You can see grains, right? It's not a single crystal material. There are many, many grains with different crystallographic orientation. So within each grain, you can see atoms are arranged in a certain way, right? Those green dots represent the atoms. So there is a grain boundary here. This is highly magnified, zoomed in, let's say the atomistic view. And what's happening? And there are dislocations in this material, defects that are there, right? Edge dislocations would be a missing half plane of atoms, would be a dislocation, right? And when you deform the material, these dislocations will move, right? And new ones may be generated, and they will interact with each other. And you need more and more force to cause it to move past each other to accommodate more deformation, etc. That's what's happening. So this is illustrating this compression. And let's see, this is a dislocation here. That dislocation moves, okay, that red dot that you see, and then it hits a grain boundary. The dislocation has to get past the grain boundary. That's another type of barrier. Not only does it have to get past dislocations within the grain, it also has to get past the grain boundary, okay? So you can see all of these interactions are contributing to strengthening of the material, right? So, and then within that other grain, it moves in a different direction because it has some preferred orientation along which slip will occur, depending on slip planes, depending on whether it's a BCC, FCC, HCP type of crystallographic structure, it will behave differently. So there are barriers, there are short-term barriers between atoms that it has to overcome. It has to overcome other dislocations like this. It has to cross them. Then it has to cross grain boundary, and then through some others. All of these things, as you're deforming from outside, is happening inside, right? And this physics-based model is trying to capture all of this. It's trying to describe using some equations. Each of these barriers that you take the linear superposition of the contribution of each of these barriers, it gives you the total strength. That's the idea, okay? All right, so without making this more difficult, I'm just going to show you this flow chart that describes what this complex model essentially does. I showed you conceptually what it's doing. So this is flow stress. There are grain boundaries, there are other dislocations that it has to get past, and there are other short-range barriers, like essentially, atoms, between atoms, there is repulsion, there's attraction, right? I mean, you have to get past those type of forces as well. And people have come up with equations to describe these things, okay? These are equations to describe essentially how this grain boundary is strengthening. This may be the most familiar to you, for some of you anyway, Hall-Petch relationship, which says that, hey, the smaller the grain size, the greater the strength of the material, right? You have come across that Hall-Petch relationship. That's an empirical relationship, really. And that describes, okay, if I have more smaller grains, which means many grain boundaries, obviously the strength will be greater, okay? up to a point. There is also something called an inverse Hall-Petcher relationship that I'll talk about later on. So this is all happening. These equations allow me to describe that. I can add all of them up, but it's more complicated than that. These grains, within each grain, dislocations can be created. They can be annihilated. Dislocations can essentially disappear, cancel each other out, okay? So if you have studied metallurgy and understood, heard about when you heat the material, what happens? You take a deep material, deform it plastically, and then I heat it. And as I continue heating, depending on the temperature, what's going to happen? The material inside, the dislocations I generated, they will relax. There'll be some recovery, okay? Recovery of that strain that you imposed, you relax the strain. That's what happens when you anneal, the material, for example. Annealing is done after deformation. So you relax the strains, that's recovery phenomenon. Then new grains may form, called recrystallization, right? Where new grains form, fresh equiaxed grains, approximately. Grains, not the deformed grains anymore. The deformed grains get replaced by equiaxed grains. And then if you continue to apply more heat, those grains that have formed newly recrystallized grains will grow, okay? So recovery, recrystallization, grain growth, you may have come across in a basic metallurgy class, right? There is an analog of that can happen purely due to deformation. Okay, that's what this dynamic recrystallization is. In other words, I can cause, through deformation, new grains to form. Essentially, by breaking apart these grains that are there through these dislocations and essentially forming new grains. I'll leave it at that, okay? If it sounds too confusing already, I won't make it more confusing. I will stop there, okay? So this equation essentially captures that. That happens to the material. And then there are some other effects, hardening, I mentioned dynamic recovery and so forth. So this is a much more complicated model, right? Now, don't get worried that you will be tested on this in this manner on Friday. No, okay? I'm not going to ask you to write these equations or whatever. That is not the point. The point is for you to understand that there are these sophisticated models that describe what is happening inside the material to what I observe macroscopically, right? In a stress strain test. That's all. Okay, so there are these barriers. I won't bore you with any more of this. You can put all of these things together. You can implement this in a finite element to solve these. The problem of deformation during cutting is not simple. This is just, I only covered so far how to describe the material behavior. I'll talk about friction as well, but you also have to be able to simulate the material separation, or the fact that as tool goes through the material, you're cutting the material, separating it, etc. All that can be done today using the finite element type of a software, right? Advantage is one example that we have used. It's a commercially available simulation software for machining. It's very simple to use. Even undergraduates can use it. My students right now are using it. It's simple enough to use that even undergraduate students can use. It takes everything. It's basically solving this complex dynamic problem, highly nonlinear problem using finite element method, okay? Discretization method. So you can input, whether it's the empirical model like a Johnson-Cook model, or this proposed, what I call unified material model. This is that physics-based model that we just talked about. You can encode this here, and then you can simulate forces, flow stress, temperature, strain rate, even grain size, dislocation density, and hardness. Last three things require this type of a model, a more complex model. Otherwise, you can't do that. Without this type of model, the empirical model will allow you to simulate all these things, except the last three, okay? So if you understand that, that's enough, okay? What do you see if you were to do this simulation? This is showing you an example. This is simulating that two-dimensional operation I showed you a video of, okay? This is a simulation. In this case, for copper, this is oxygen-free high conductivity copper. It's just a model material. It's used for copper wires, electrical wires, etc. It's well-characterized material. That's why we picked it. And This is showing you that I've changed the cutting speed. Okay, I can simulate the chip formation behavior as a function of speed. You can see at different speeds, as you increase the speed, the chip becomes thinner. The colors represent, in this case, actually in this case, this is using the more sophisticated model. Okay, it's using that more complex model. So it's simulating the chip form, but it's also simulating the grain size distribution due to refinement of the grains due to this deformation, etc. Okay, and it's also simulating the dislocation density distribution inside the material, right? So it's simulating those kind of things as a function of both grain size, dislocation density. The top row shows you how the grain size changes in addition to the thickness of the chip and the shape of the chip. And this one shows you the same thing for the same conditions, how the dislocation density changes, right? Using this more sophisticated model. Now, yes? No. Mm-hmm. Well, not explicitly, not like crystal plasticity models, right? So they are still continuum scale models. They require some data for sure, actually. Again, I point you to the papers that you could give you the details, right, of what all's required. Let's look at force. I want to be able to produce cutting forces. That's a more easy thing for us to all understand, right? So this is showing you there are two components of force. This is a orthogonal cutting operation, simple like taking a knife and removing a layer of material. So force in the direction of cutting, force normal to the direction of cutting, right? Those two I can measure using, yesterday I think mentioned that there are these sensors available that called piezoelectric force dynamometers that you can place or mount the workpiece on it and cut, and you can measure the forces. So these were measured that way, okay? Measured by somebody else, collaborators of ours. Actually, Professor Chandrasekhar is a graduate of IIT Madras, really, really highly accomplished researcher, and his former student. They shared this data with us for this material, and we simulated, right? So it's showing you that I can simulate fairly accurately as a function of cutting speed, the two components of force, right? That's useful. I can simulate that. I showed you only these two things. You can simulate temperature distributions and all of that you can do, okay? So you get some idea, hopefully, of the complexity of trying to model a simple two-dimensional cutting operation. Now trying to do this for turning, milling, drilling, where the geometry is even more complicated in 3 dimensions, okay? The principles are the same, right? And you can do it. These commercial codes actually allow you to simulate three-dimensional cutting, but they're much more complicated, much more computationally intensive, okay? Leave alone using that more sophisticated microstructure-based model, okay? Even if you don't use it, it takes a lot of horsepower to solve those problems, okay? It can take days to simulate few revolutions, or hours, for tens of hours for sure, okay? So that's where we stand today in terms of these type of things. Now, I only talked about constitutive data and models. Yeah, there are many other aspects that these slides point to, but in the interest of time, let me touch upon a few other things. And then we will stop, and then we'll rather discuss, because I feel some glazed look on your eyes. So I feel I'm not getting through to you. So that's not very useful, okay? So I want this to be, it's a course. You should be able to at least walk away thinking, not thinking that I didn't understand anything, or at least understood something, okay? That's more important. So I mentioned friction is important. So here also I won't belabor anything. All of you understand that frictional phenomena are what is happening that is responsible for the frictional resistance between two surfaces that are normally loaded and in relative motion is dependent on the actual microgeometry of the surfaces. In other words, no surface is perfectly smooth. No surface, okay? The smoothest surface that you think is smooth is not smooth. You just need to look at it at a certain magnification. You will see it has its roughness, okay? Whether that roughness matters or not is a different question. Every surface is rough, okay? So what is responsible for friction? there are these mechanisms, okay? Contact between the asperities. Asperities refer to these roughness peaks and valleys on a surface at some degree of magnification. And when you take two surfaces, this duster is sitting there on the surface. If I ask you what is the contact area between the duster and the surface, what would you say is the contact area? Contact area of the base of this duster, you would say, right? Which is the length times the width of this duster. Well, that is really the apparent contact area. It's not the real contact area. Why? Because neither of these two surfaces is perfectly flat or smooth, right? It has, if you look at it carefully at high magnification, there are these peaks and valleys. So the real contact area is the contact between these opposing peaks and valleys, right? When you have very, very smooth surfaces, then the real area of contact and the apparent area of contact are almost the same, right? So in machining, between the chip and the tool, the contact area is almost the same. In other words, it's like the real area of contact is equal to the apparent area of contact. The contact stresses are so high that adhesion, is so high that these asperities will deform plastically and contact becomes almost like these, they flatten and you have, the real area of contact approaching the apparent area of contact. Under those conditions, the frictional phenomena are much more complicated, okay? Your simple Coulomb friction doesn't describe what is happening. Coulomb friction may describe what is happening as the chip is moving away from the face of the tool at the tail end of contact. But right near the tip of the tool, where you saw the chip, in that video, the conditions are very different. So the apparent friction coefficient can be as high. What is friction coefficient? Tangential force divided by the normal force, right? If you were to compute that quantity, in this case, for machining, you'll get values much greater than 1. Well, for those of you from physics, basic physics and mechanical design, you don't deal with coefficients of friction greater than 1. What does it really mean? Right? It doesn't. That's why it's the apparent coefficient of friction. So the contact conditions are very severe because of severe plastic deformation. And so modeling the actual contact conditions between the chip and the tool is not a simple task. Okay? People approximate it as some approximate Coulomb friction, or more sophisticated models actually will model how that normal stress and the frictional stress changes as a function of location, okay, and temperature. There are different ways people do this, okay? So this is not easy. Here are different types of models. This is your Coulomb friction type of a model. The shear stress divided by the normal stress, okay? That is kind of the contact stress. If you can predict the frictional stress as a function of strain rate, and temperature, normal stress as a function of strain rate, and temperature, then you can approximate the frictional conditions between the chip and the tool using this ratio. This is nothing but, analogous, and then, so this is like your Coulomb's law in some sense, okay? That's what this is, effectively. But this friction stress, like frictional tangential force divided by normal force, this is in terms of stresses, the same thing, okay? But except we know that the tangential stress and frictional stress, normal stress change as a function of strain rate, and temperature. So it's more complicated. There are more sophisticated models like this, okay? You can describe much more sophisticated models that people have tried and used, okay? Most software that will model it will use some combination of these two here, this type of a model, okay? Like a friction factor based model, where the shear stress between the chip and the tool is some factor times the shear yield strength of the material, K, okay? That is the yield strength of the material in shear. Just like yield strength of material in tension and compression, you can also do a shear test and determine the yield strength in shear, okay? That's what this K is. All right, but the reality is it's something like this. The normal stress varies like this, at this point where the chip leaves the free surface of the tool, this is the tool here, it goes to 0. The shear stress is very high. It's approximated as being constant up to this point, and then it drops. And both go to 0, where the chip leaves the face of the tool. It curls away, right? You saw in the simulations. These type of models have been used, and still reasonable simulation accuracy can be obtained, okay? All right, you know what? In the interest of time, I will. So even characterizing, even getting the parameters of these models, friction models, is not simple because of how complex friction is in machining, okay? So people have been working on finding testing methods, simple tribological tests that people use that you might find in the design handbook, value of coefficient of friction between two materials, right? That you might use for design, mechanical design, are no longer adequate for this. So you need testing methods that will describe the frictional conditions that are representative of what happens between the chip and the tool. So to do that, people have come up with different types of tests where the contact stresses are made very high, because that is the case between the chip and the tool. Think the chip is very small. It's contacting over a very small area, even though the force may not be high, but it's distributed over a very small area. The contact lengths are very, very small. So the contact stresses are extremely high. So you have to simulate those type of contact stresses, right? And speeds and other things, relative motion. So people have developed different types of testing configurations to capture the frictional conditions between the two materials, the tool and the workpiece, and shown that these are more representative of what happens in practice. And so you get better simulation accuracy, okay? That is your takeaway message. There is a lot on this slide in terms of specific methods. That's not as important, okay? What is important is that there are methods that for you to be able to use if you have to. Okay, there are many other factors that influence friction, okay? So people have found in machining that, we use coolants. We were talking about coolants, lubricants, and etc. even yesterday. So while it is debatable whether the coolant really enters the chip and the workpiece interface, right? I argue it doesn't, okay? But let's say it's debated point still, right? But the actual forces do change. So there is an effect, right? So to capture that effect, and it turns out that when you take measured forces and compute the coefficient of friction, it's different. The apparent coefficient of friction, it's different. So it varies with the material, tool workpiece material pair. It varies with the cooling mode, how you're cooling the material, whether you're adding a coolant, flood coolant, misting, or whatever type of technique. So they influence the frictional, this is the apparent coefficient of friction as a function of cutting speed for different pairs of materials cooled in different ways. Changes. So you have to be able to capture this, right, in your friction model. This is the same thing, somebody else's data, but saying the same thing as a function of sliding velocity and cooling medium, the friction coefficient changes. Again, this is saying the same kind of thing. The type of lubricant you use matters and so forth. So it's well known that this apparent coefficient friction changes with velocity. It changes with cooling. It changes with the materials involved. Materials shouldn't be surprising. Obviously, it'll change, right? Two materials, different materials will exhibit different frictional characteristics. All right, so people have incorporated these types of things into finite element software and shown that you can simulate, with some degree of accuracy, the forces, chip formation, chip thickness, and things of that nature, right? People have also tried to incorporate it to predict tool wear. Some of these commercial codes will allow you to simulate tool wear. But if you ask me, I think those tool wear models are very simple first order models. You can't rely on them. Tool wear is a difficult problem. Actually, in my opinion, it's a very difficult problem because there's so many stochastic aspects of wear phenomena that to predict tool wear from first principles, even though you know that there are fundamental mechanisms that are responsible for that wear. It's adhesive wear or abrasive wear or it's diffusion wear or whatever wear mechanisms that are understood. What combination of these mechanisms is responsible for wear? Nobody knows unless you calibrate. For every tool workpiece material combination under different conditions, different combination of these mechanisms may be playing a role. And if you think in practice, when you use a cutting tool, you may use it to cut this material, then some other material, or even one material that you may be cutting, you're using a range of feeds and speeds, because if you plan a tool path in a milling operation, different features are being cut at different speeds, depths of cut, etc. So just simple description of tool life as a function of one speed and one, it is not enough, right? So it's not simple. Okay, so I'm skeptical of what these models, even if they have them in software, can really do. Okay, I wouldn't rely on it. Force prediction, fine. Temperature prediction, reasonable. Okay, these kind of things are fine today. So that suggests to you that it's still an open issue of how to predict tool wear, okay, in a practically relevant manner. All right, what else? The last part of it is microstructure data and models, okay? So this is a complex problem, complex issue. When you machine, machining from the surface looks very simple. You cut the material, you can do on a lathe, a turning operation, or a milling operation, or a drilling operation. But as I just described to you, when I was talking about the physically based models, what is happening inside the material? Dislocations are moving, new grains may be forming. The actual mechanical properties of that material after it's been machined are dictated by the microstructure. And the microstructure prediction is still a very complex problem, right? We have, in my opinion, in machining, and in machining especially, because it is a severe plastic deformation process. You're deforming the material under extreme conditions. And under those conditions, microstructure evolution is quite complex. People have studied it. All that you see on this slide are showing you a study where they tried to investigate what is happening to the material inside. These are all snapshots of very, very small regions taken using transmission electron microscopy, which is very, very, time-consuming type of microscopy to do at very, very small scales. What is happening? What kind of dislocations? What kind of defects are there? What is really happening to the material as a function of strain and the rate at which I'm deforming the material? So people have experimentally tried to do this to try to gain an understanding under what conditions will I produce certain types of microstructure in one material as a function of shear strain. Shear strain can be controlled by the cutting parameters. There's a relationship that you can show that by changing the tool angle, by changing the feed, I will change the shear strain. So this is y-axis is connected to the cutting parameters that you select. Deformation rate is also related to the cutting parameters, the cutting speed, okay? Determines at what rate I'm going to deform the material. So as a function of cutting parameters, what kind of a microstructure will form? That is difficult to even understand. We have to do experimentally, we have to try to do. So people have done a lot of work in this area. It is not that simple to model from first principles. Even though I gave you an example of this dislocation mechanics-based model, we have tried using it, and I'll show you what happens when you do something like that. But I want to make the point here that this microstructure evolution in a machining operation is very complex phenomena, and we are far from the point where we can describe everything from simple equations. No, we cannot. We're not there yet. Because you can produce nanocrystalline grain structures. You can produce very, very highly refined grain structures using machining. Simple machining, right? You produce nanoscale grain structures, extremely high hardnesses, etc. So, which can be a good thing, but doing it experimentally versus being able to model it, that's still a challenge. People have done it experimentally and shown. But what do I want? What do you want as an engineer? I want to know, if that's what I want to do, how can I do it? you want to answer that question. I don't have a way to tell you how to do that unless you have a model that can describe it, right? So that's the complexity. Okay, let's skip this. There are different ways of characterizing. This is only talking about the different types of characterization methods. Modeling. Okay, so it's not that people haven't tried at all. So I told you this type of a model, grain refinement model. There are models that I talked about that are dislocation mechanics based, or people have also tried what I referred to as crystal plasticity models. These type of models people in mechanics literature use, but at the scale at which, under the conditions in which machining is being carried out, it's difficult. At least I haven't, there's some attempts have been made to use these crystal plasticity models, but these are just a few crystals being deformed. But when you're machining, you have a large volume of metal with many, many, many crystals in there, right? Simulating that is not that simple, okay? Or it's computationally expensive. But people have tried. People indeed have tried. I'll show you something. I'll give you an example. I'm going to skip this. This is an example. This is to kind of make the point that I want to simulate chip formation in cutting of titanium. Titanium is a superalloy. Turbine blades are made out of titanium alloys and many other things, biomedical devices, as we discussed last time. This is showing you a simulation of what happens to the chip. The chip looks very different. It has these, it is called what is called a segmented chip, which exhibits shear banding. That is, there are bands of high strain and low strain in the chip, very periodic. You see, the blue regions periodically occur. They are regions of low strain. They have undergone very little deformation. These, what appear to be light green regions in between those blue regions, they are regions of very high strain. Okay, severe plastic deformation in those regions. So it's a complex phenomenon that happens in these certain types of materials, such as this. Generally, materials that have low thermal diffusivity, okay, such as titanium, Inconel, even some steels, okay, will exhibit this type of behavior. This type of chip formation can be bad because this means that the force, high strain, low strain, high strain, low strain, every few milliseconds, okay, means the force will also vary. High strain, material is stronger, right? Stress-strain relationship. High strain, higher stress. So material behaves stronger. Then next, immediately after that, low strain, materials after. So you will see oscillating type of a force behavior in this process. You have to be able to simulate that. That can be bad also for the process. You can excite the machine tool resonant frequency, for example, and cause resonance and vibration, and all kinds of problems can occur too. But it happens. So I want to be able to predict it. Now, let's not worry too much about the details here. This is telling you that I need, in order to be able to predict this phenomenon, you have, one way to do that is to account for what's happening in the material, is dynamic recovery, dynamic recrystallization, which I kind of referred to earlier on, and something called a softening effect, which is an inverse Hall-Petch effect. Hall-Petch effect says smaller the grain size, higher the strength. But that fails beyond a certain point, okay, in some metals, right? Below a certain grain size, at nanostructured grains, it's been shown that the opposite thing happens. It starts to soften. And that occurs because it turns out of grain boundary sliding and those type of effects, much more complicated effects. But anyway, you can account for this somewhat semi-empirically, which we have done. This is the Hall-Petch relationship here. And this is the inverse Hall-Petch equation, which is saying that as I decrease the grain size, right, you can see here, if it is purely Hall-Petch equation, the stress increases as I increase the grain size or decrease the grain size, okay? But beyond a certain grain size, it starts to drop for certain metals. That's the inverse Hall-Petch equation. And so we can capture that. There is real data showing you that type of behavior here, leveling off. So that's the inverse Hall-Petch equation. So we fit a model that captures this behavior, right? And incorporate it into that more complex model, right? Which accounts for interaction between dislocations and grain boundaries and all of that, right? we have accounted for it. And this is that model. And more importantly, let's see if I can run this simulation. Oh, no, maybe not. But okay, let's go straight to the results themselves. Okay, the simulation is not working. I don't know what happened there. But this is showing you the ability to predict it. So we can predict. This is the actual chip. This is the simulated chip that shows this alternate region of high strain, low strain, high strain, low strain. We can actually predict the thickness of the chip, how it changes, right? This is what this is showing, right? As a function of cutting speed, I can predict it reasonably accurately, okay? The chip thickness variation. Let's see. I can also predict what is going on there. So here is looking at a gap between the high strain region, this is the high strain region here, between two segments of that chip, right? There I can predict what the grain structure is. The reason this region is highly strained, when it's highly strained, the grains are going to be deformed a lot, right? You take a grain and you deform it excessively, you would expect to break up that grain somehow, right? Into much finer particles, if you want to, for simplicity. It's not a technically accurate way of describing it, what is happening, but conceptually that is what is happening. So indeed, you can simulate that, okay, using these type of models. And that's what we have done here. So you can also simulate, where there could be cracks and so forth, but without worrying about it, the point I wanted to make is that there is a way to simulate some aspects of microstructure in using these type of more sophisticated models in machining. Okay, that's enough of complexity of again, I want to make sure I don't lose you totally and you say, okay, well, this is, I don't know what the heck he's talking about, right? At least you want to understand the concept here, that, or at least have a sense of the state of the art. What can be done. Now, these types of microstructure prediction capabilities don't exist in commercial software. They don't. You have to build it yourself into those commercial softwares, which is what we did. All right. So where does it put us? Okay. And then we will leave time for Q&A discussion, general discussion. So we have made a lot of headway in modeling of machining operations. And much of what I showed you is still just 2D simulations. Industry wants you to be able to simulate real practical operations. You can do that, but not in a computationally efficient manner today. It takes you hours or days, or tens of hours, and days to do that. So more work needs to be done to figure out ways of course, you could argue, I will use a high computing cluster, like a supercomputing cluster to be able to run this. But even then, it's expensive to do, right? So much more work needs to be done. Predicting tool life is not easy, even now. The range of materials, many of these softwares have several tens of materials, tool material properties, workpiece material properties. But if you're trying to machine something very different, then you have to build all these constitutive models and incorporate it yourself, right? Those are required things before you can use these simulation tools. So there's still quite a bit of work to be done to bring this technology to the point where it can be, it's practically useful. I'm not saying it's not useful, but it speeds up the process development or product development time, because you are not doing this only using experiments, which is very time consuming and expensive. You cut all of that significantly by developing a basic understanding, narrowing it down, then go do some experiments. So that's the utility of these types of models today, okay? That's it. I am going to stop here, okay? And we have time, 20 minutes, for some discussion, okay? I know there weren't many questions. I'm not surprised. Maybe some of this is much more involved than and I'm going to sit because my feet are hurting. So questions, yeah.
Sir, has there been any efforts to include the effect of lubrication in these models?
Yeah, including coatings actually.
Yeah.
So some of these softwares will allow you to specify coating. Fundamentally, though, how they are incorporating it is they're essentially changing the coefficient of friction, the apparent coefficient of friction. And that's the way they are doing it. Even coolant, they don't explicitly model, they don't integrate computational fluid dynamics simulations into this. As it is, this is computationally expensive to do. People have done CFD simulations for understanding fluid flow in cooling characteristics, etc. But the way these softwares will allow you to do is to change, specify the boundary conditions, the heat transfer, convective heat transfer boundary conditions, specify change in friction coefficient if that happens. That's the way to do it, whether it's because of coatings or whether it's because of coolant. That's what you can do today. Yes?
Sir, what are some of the common packages which is used for doing these sort of simulations?
So there are a few. So one of the one we have worked on and used, you can build your own. Initially, we were building ours using Abacus, which is a general purpose finite element simulation software. People have done it using ANSYS, but it's much more difficult to do. They are not designed to do it. Today, Abacus latest versions have some other features that allow you to do this, because again, this is a severe plastic deformation problem. So things like element distortion, those kind of challenges you deal with, right? Now, commercial software dedicated for machining simulation, the one we have used is Advantage. Advantage is a software that is developed by a company called Third Wave Systems, okay? It's a company called Third Wave Systems. Oops. And they are actually you can look them up. In Minneapolis, Minnesota, that's where they are, a relatively small company, but they have been around, and their software is used by most major cutting tool manufacturers and end users, aerospace companies, etc., for process development, optimization, and stuff like that. Their software is one that is designed for machining only, okay? 2D and 3D. And then there's also Deform, which is the other Deform is another software. It was actually developed for metal forming simulations, which also involve finite plasticity type of problems. And so Deform can be used for machining also, okay? Beyond these two are the most widely used. People have tried using Forge 2D, Forge 3D. They're all forging, adapting it for doing machining simulations, but they're really not designed for it. The one that is specifically designed for machining is Advantage. Other questions? Maybe this is too much stuff, too much detail and perhaps beyond some of your comprehension, at least for the undergraduate students. But at least you get an appreciation for where things stand today, what can be done, what cannot be done, as far as being able to simulate simple machining operations that you take for granted when you see them. Hopefully you walk away with the appreciation for the complexity of what is going on in those processes, that even to this day we cannot describe everything accurately, sufficiently accurately anyway. No questions, today? Everybody's tired. Okay.
Good afternoon, sir. My question is from nanocrystalline. So my question is, what technique are commonly used to observe nanocrystalline refinement at the surface?
Well, I mean, I mentioned transmission electron microscopy. Okay, even an optical microscope actually will, in an optical microscope, if you looked at the chip, like a titanium chip. Okay, wait, let me go here. So this region that you see here, this is a scanning electron microscope. It's not an optical microscope image, but this is a highly, you can see the grains here. So it's almost as if this material didn't undergo any deformation. This is the original. This is in the chip. This is in the chip. The chip means it's already cut, but nothing happened to these grains. It wasn't sheared. But in between these segments of the chip, there is this region of very narrow region of you cannot see grains there. So whatever grains were there are highly deformed. So deformed that you can't resolve the grain structure. So that is an indicator that there is something more happening there. And then you need to go deeper. You need to go to a much higher magnification tool, such as looking at transmission electron microscopy, for example, or even electron backscatter diffraction, EBSD, okay, which you can do on a SEM. Okay, you need to have a EBSD capability on that SEM, and it will tell you grains. It may be able to resolve grain structure, refine grain structure in that region. But the sure short way would be transmission electron microscopy, actually. But even in these regions, when you see something that is very, very white, these regions can appear very, very white. The reason it appears white on an optical microscope, which is easy to get access to, is because the optical microscope is unable to resolve it. That to me points that there may be something there, maybe nanocrystalline structure, possibly. It could also be amorphous, but possibly nanocrystalline. Then you have to dive into some other deeper, more higher magnification probing technique, like transmission electron microscopy or EBSD.
So what are the factors mostly influence this in the refinement during machine?
Can you repeat your question?
So what are the factors most significantly?
Most significant factor.
Yeah.
That's a tough question to answer because, like for example, in titanium, right? It is a function of the process mechanics. In other words, it's a function of the behavior of the material, right? This material is a low thermal diffusivity material, which means that it cannot conduct the heat away fast enough. So heat accumulates in a region, in a narrow region, and material softens significantly. That is one theory, right? And then you have what is called adiabatic shear banding. Heat cannot escape, adiabatic effect, and then deform because it softens so much there, it deforms a lot. Very high strains are generated in that region, right? So that the thermophysical properties of the material is one factor in this case, like thermal diffusivity. But it's also a function of the cutting conditions. But thermophysical properties of the material play a pretty significant role. Okay. Also, the strain rates matter. Strain rates matter. How fast you're deforming the material. Okay. Because sometimes for the same material, under certain speeds, you will not see this phenomenon. Like in certain steels, you only see the step of a severe plastic grain refinement at very, very high speeds, not at low speeds, right? So it's a bit more complicated. I can't give you one answer that, hey, this is under this condition, this is the only factor that matters. But I'd say the properties of the material and the deformation rates are two important factors. Okay.
So as the last questions, so what are those actually in data we are seeing that accident? Is then we can do any validations or something? How we can validate?
Well, this is validation. What this is validation showing you basically the dimensions of the chip. This S1 is this width, S2 is this, S3 is this dimension. Okay? So these have been measured and predicted and compared. That's one way. Measuring forces, comparing is another, right? So this is also looking at the segmentation frequency. That is the frequency of these high strain, low strain regions. They occur periodically. So you can predict that because you can predict this, right? This, and compare that to what you observe experimentally. So these are all ways. Now, if you can measure temperatures, that would be another way to verify. But what is easy to measure? Forces are easy to measure. Chips are easy to characterize. Those would be the two easiest things.
Thank you, sir. I'm good in.
Yes.
So when we talk about the friction models of this, so do we need to improve the roughness of the
None of these models actually include roughness. I mean, to be able to simulate frictional phenomena, including roughness, people who in tribology, when people do models for modeling of hydrodynamic lubrication and things of that nature, they try to incorporate the effect of roughness. But this type of modeling here, I'm not saying there is no value, but I question the computational effort required to account for that level of detail. I can't even describe it macroscopically. I mean, if I can describe it using some simple approximation of how friction changes as a function of the key parameters and incorporate into this model, and it's enough for me to predict reasonably well what happens in the process, that is better. It's simpler, right? So I'd argue that simplicity is better. Yes, accuracy is important, but a simple way to capture the accurate information is more important here, because friction is only one aspect. It's an important aspect, but it's only one aspect of the overall thing that you need to model here. Material modeling is also there, etc. Right? So no, I don't know of anybody who tries to incorporate that level of detail in a friction model. Almost always it's modeling the friction. Let me say, where did I go? Like this, these type of equations. Okay, these are many different types of friction models people have tried. Okay, to describe. It's still a area of ongoing research. There are people still trying to say, okay, well, what's the best way to describe the frictional conditions and model it? Okay, but you can get away with, in most software, there'll be this combination, this type of a model. For a portion of the contact from here to here, maybe from here to here in this region, you will use this type of a friction model, tau equals m times k. And then beyond this point, where the shear stress starts dropping, normal stress starts dropping, use a standard Coulomb friction model with a coefficient of friction, right? Because the normal stresses are very low. Yeah. So that is very common to use. Yes.
Sir, I observed that you kept the rake angle to be 0 and you changed the speeds, the cutting speeds, and there were optimized chips with different, in increasing the speeds, right?
Mm-hmm.
Is there any work going on, especially on the chip formation, when it comes to chip formation by optimizing parameters or optimizing groove geometry of the inserts?
There has been a lot of work. I mean, I showed you one result where the rake angle was 0. But we have, other data where the rake angle is varied. So there's a lot of work that has been done in the literature where people have changed the rake angle. Professor Chandrasekhar's work, they vary the rake angle often because that's one way to vary the strain in the material. So indeed, there's work done. And these commercial softwares, you can change the rake angle. It's not a problem at all. Yeah.
Like optimizing the chip being formed can also greatly impact over the microstructures and things, right?
I don't know how to answer that question. The reason I struggle with that is because what you want, yes, chip formation is behavior is related to how the material deforms, and how the microstructure is a function of how the material deforms, right? So yes, by controlling the chip formation behavior, you will produce a different microstructure, more than likely, but so that is a reasonable statement to make, a correct, accurate statement to make, right? But exactly how to, I can't give you an answer. Hey, if you produce this type of a chip, this is the kind of microstructure you will produce. That's a harder question, harder problem to answer, right? But yes, does the different chip formation relate to different microstructure? Probably, yes. Does that help answer your question? Yeah. Okay. Three more minutes.
General question.
Yeah.
So, are you involved in any digital twin development of these, like use cases, modeling?
I am not myself. There are people who are interested in building these type of digital twin models, but let's say I'm a bit skeptical, only because see the complexity of even simulating simple things. Now, you might argue that, okay, you know what, I can take a simple model that is not very accurate, and maybe I can compensate for what is lacking in these models with data, and that by combining the two, I can get a more accurate prediction of force, simple things. I think there is merit, in doing that. That to that extent, digital twin, if you want to call that digital twin, fine. But trying to, eventually, if we can advance this understanding and modeling to the point where I can solve these things efficiently, like a three-dimensional operation, simulate in real time, like you're doing, which you cannot do today. If it takes days for me to simulate 2 revolutions, I mean, what point is it to have a digital twin, right? So you want a digital twin to be simple enough that can run very quickly and take some data in real time, or at least quasi-real time, and update your model and give you some knowledge of the process response that is accurate enough for your purposes. At that level, it's okay. But can you do for microstructure simulation and so forth? At least not in real time. Unless you build surrogate models that are empirical models. You run many of these simulations separately, and you build some sort of a regression model that is simple to run and quick to run, that you use with data in real time. There may be ways like that where you could achieve computationally efficient models, perhaps. But I don't know how accurate they'd be. But I don't know why you would want to do that with microstructure type of models anyway. I mean, I think it's okay for forces, things of that nature. It's okay. You should be able to do that. That's my personal opinion, by the way. Okay, don't take that as set in stone. It's just my personal opinion.
Any more questions?
Is there we can implement the machine learning for predict that that one? I mean, what we are giving the surface. If we implement the experimental data into machine learning, so we can create some model and we can predict that things. So
sure, you can build purely data-driven models. Sure.
So okay.
You can build purely data-driven models and use that as some sort of a digital twin for whatever purpose that you want to. So you could do that. But, again, that may be of practical use, but as scientists and, researchers, okay, we want to develop an understanding that is generalizable, right? That doesn't just work for that one instance. In practice, I understand what you're saying. Yes, there's value. Company cares less about being able to simulate everything. They want to know, am I producing the part correctly, and how much information do I need to produce the part correctly? For that purpose, it may be adequate to what, to do what you're describing. All right.
Yes.
Thank you very much. I hope it was not too boring because of the kind of the level of content that was involved. I'm sure it was to some degree, but hopefully you walked away with enough of an appreciation for it. Tomorrow and day after we'll talk about two different topics. One on robotic machining, very different, still machining, but robotics, industrial robotics. And then we'll talk about finally machine learning, and decision making. Okay? All right. Enjoy the rest of your day.
Thank you so much, Professor.